It was a partially cloudy but otherwise pleasant September day of 1909 in Berlin. A sizable crowd was assembled at the Tempelhof Green, the old parade ground of the Prussian army. They were there to see something incredible. A machine flying with a man controlling it. Orville Wright took off and flew for a few minutes above the crowd's heads, amazing the spectators. In that crowd, there was a 15-year-old boy whose life was going to be changed by what he saw that day. Alexander Lippisch was born in 1884 in Munich. He studied art following the father's tradition. When the First World War erupted, he finally had the opportunity to pursue the bug for flight that hit him the day in Berlin. He didn't manage to become a pilot, but he served as an observer, a photographer, and a mapper. After the war, he went to work for Zeppelin, demonstrating a real talent for aerodynamics and the ability to think out of the box. His most famous creation is the Messerschmitt 163 Comet, the famous rocket-propelled tailless interceptor. But this is not relevant for our story. What is relevant is that Lippisch was on the list of the important scientists and technicians to be captured and taken to the United States at the end of the war in the context of the Operation Paperclip. So he settled at White Sands Air Base, but soon he started receiving visitors from California because someone was very interested in his work. Convair. Welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. Please stay with me till the end because the stuff that we discuss here are not found anywhere else on YouTube. In the late 1945, the United States Army Air Force, the predecessor of the United States Air Force, was interested in a supersonic point interceptor. At the time, Consolidated Vultee, the predecessor of Convair, proposed a solution with swept wings. At first, the propulsion should have been mixed rocket and turbojet, then a ramjet was proposed. However, none of these solutions demonstrated to be a viable approach to the problem once tested in the wind tunnel. And honestly, the propulsion that was chosen wasn't ideal at all. Convair designers were back to the drawing board. In the meanwhile, together with Lippisch, something else had traveled from Germany to the USA. In the last few months of the Second World War, Lippisch was working on a supersonic ramjet-propelled point defense fight. His experience with delta-wing gliders and tailless designs brought him to conceive a strange and sort of alien-looking configuration. To test this configuration, the construction of a glider known as the DM-1 was still ongoing when the American forces reached Munich. The US military government recognized its own potential in the design, financed the construction, which was completed in November 1945. The DM-1 was then shipped to Langley Field in Virginia, where it was extensively tested in a large NACA wind tunnels. At the beginning, it showed a large drag, surely not suitable for supersonic flight, so NACA engineers started making changes. They reduced the vertical fin, but most critically, they adopted a sharp leading edge and a thinner airfoil, which produced the desired drag reduction. It was here that, for the first time, the classic delta-wing vortices were noticed and recognized as a stable and regular feature. We don't know how and why Convair designers came to know the results of Langley tests, but the chief of aerodynamic research, Ralph Scheck, started considering the delta wing as a possible solution. So he has to be received by Lippisch himself to better understand the idea. Two men met at Wright-Patterson Air Force Base, and Schick came back convinced that the delta wing was a solution to their problem. But another problem was that nobody had ever built a delta wing fighter, so Convair proposed to build a demonstrator. The United States Air Force accepted, even because in the meanwhile the interest for a point interceptor was considerably reduced, and so the demonstrator was named XF-92A. The XF-92A had a quite bizarre look. The wing was what we would call today a classic delta. The vertical fin was a small delta wing too, but almost everything else was recycled from other planes, making it a sort of a Frankenstein monster. Even the fuselage design was the classic fuselage design of the first fighter jets, with a round intake on the nose and a long tailpipe for the engine. The plane first flew in September 1948, and after Convair tested that it was acceptably safe to fly, it was handed over to the United States Air Force in September 1949. The Air Force assigned no other than Chuck Yeager to the program, with the purpose of investigating the wing behavior. And Yeager delivered. He took the plane beyond the sound barrier for the first time, reaching Mach 1.05 in a shallow dive. Then, while landing, he pulled the nose up to slow down, but to his surprise, the plane did not show any sign of stall and it reached 45 degrees of angle of attack while still being fully in control. He had discovered the effect of the delta wing vortices, something that Yeager is not famous for. The plane kept flying till 1953, improving the knowledge of delta wings. The data acquired with the XF-92A fully persuaded Convair that there was a potential to be developed. The good behavior at transonic speed and at the same time the good behavior at slow speed was something that no other wing platform seemed capable of achieving. And this conclusion was very important for the company, because another challenge had landed on the table of Convair designers. At the time, it was called the Ultimate Interceptor. Its real name will be the F-102 Delta Dagger. In the late 1940s, the appearance of the first Soviet strategic bombers like the Tupolev Tu-4 prompted the United States Air Force to launch the development of a series of interceptors to protect the territory of the United States against this potential threat. Initially, the development of the Lockheed F-94 Starfire and the Northrop F-89 Scorpion was accelerated to meet this need, but it was clear that they were just a temporary solution. So, in October 1948, a senior Air Force committee recommended a project to build the Ultimate Interceptor, scheduled to enter service in 1954. That was the name they chose, the Ultimate Interceptor. In January 1950, the Air Force officially launched the program, but did something different than the usual. While the whole program was named WS-201A, the requirements were split in two. The requirement MX-1179 covered the armament and the fire control. The requirement MX-1554 covered the plane itself. MX-1179 was won by Hughes in July 1950, and we will come back to it. MX-1554 was the subject of a tough competition, with all the American aeronautic world eager to win the race. In the same July 1950, the Air Force reduced the participants to Lockheed, Republic and Convair. Lockheed dropped out, they had a lot on their plate already. Republic took a very long time, and in the end they were only capable of producing a mock-up. Convair, on the contrary, had an extremely clear vision about this project. Welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. Please stay with me till the end, because the stuff that we're going to discuss is very hard to find on YouTube. In the years immediately after the war, Convair became the first American aerospace company to acquire experience with the delta wing. With the help of the NECA and the mentoring of the father of the Delta Wing, Alexander Lippisch, they built the XF-92A. It was an experimental Delta Wing aircraft that allowed them to accumulate experience with the new configuration. On the basis of that experience, Convair was sure to master the technology to create the outstanding interceptor that the Air Force wanted. In November 1950, Convair was given the go-ahead for the development of the prototype, the F-102. As it often happens with the development of new technologies, problems and delays happened. The engine should have been the Curtiss-Wright J67 derived from the British turbojet Olympus, but its program was late, so it was replaced with the Westinghouse J40, which turned out to be a fiasco and it was scrapped. So in the end, the Convair settled for the Pratt & Whitney J57 as a temporary measure. The fire control system that Hughes was supposed to build was not ready yet, so it was replaced on the prototypes with a less capable unit called the A9. However, despite all these setbacks, the prototype was built and it flew for the first time on the 23rd of October 1953, only to crash 9 days later because of an engine flame out on takeoff, with the pilot luckily ejecting to safety. There had been no much time to test the plane, but the few data acquired were not really promising. In any case, Convair used the time allowed by this setback to build an improved prototype, which finally flew the 11th of January 1954. When Convair engineers finally put the plane to the test, they were not prepared for what happened. The major advantage of the Delta Wing was its benign behavior at transonic speed, if compared with swept wings or even short and stubby wings. The F-102 was designed to be supersonic to quickly intercept the incoming bombers. Such beautiful and slender aircraft with its futuristic delta wings was expected to easily pass Mach 1. Unfortunately, it did not. Convair engineers were shocked to learn that the maximum speed in level flight was Mach 0.98, way below the specification. The drag seemed to be much higher than expected, slowing the aircraft down. And since when it rains it pours, the J57 engine was not producing the expected thrust. It was a frantic back to the drawing board because the survival of the program was at stake. Luckily, they came across an idea that had the potential to save the day. And actually the new idea had a name, Richard Whitcomb. Richard Whitcomb was a NECA engineer who in 1952 had come up with a bizarre idea. He made a lot of aerodynamic experiments with slender aerodynamic bodies with wings, but with variable cross-section, and it seemed that sort of pinching the body in the middle like a bottle of Coke was reducing the transonic and supersonic drag. After a lot of work, he came up with a sonic area rule that seemed to offer guidance for the project of a transonic aircraft. Actually, to be fair, the area rule might have been discovered independently at least a couple of times in the 40s, but the official historiography gives the credit to Whitcomb, who we know for sure did it independently. Convair offered Whitcomb a generous contract to help in the redesign of the F-102 prototype. But before going on with our story, we need to understand what the sonic area rule is. The high drag experienced by the F-102 seemed to come from the interference between the wing and the fuselage. Classic methodologies to calculate the total drag of a plane added the fuselage drag to the wing drag. It was well known that there was some extra drag due to the interference between the two, but at subsonic speeds it was almost negligible and nobody really cared. However, Nearing Mach 1, the extra drag was sharply rising beyond the expected values. And also, quite puzzlingly, on swept wing planes, the wind tunnel test had shown that a shockwave was occurring toward the tip of the wing, which seemed to contribute to the extra drag, and it also could create issues to the control surfaces. Of course, near the speed of sound you have shockwaves that generate extra drag, but of course, nearing the speed of sound you have shock waves that generate extra drag, but why should you have one there? And why this extra drag seemingly coming out of nowhere that could only be attributed to the interference between the wing and the fuselage? Whitcomb's stroke of genius was exactly to understand what was really happening. One step back. Why quick planes mostly have swept back wings? The reason is to delay and limit the effect of the air being compressible, which means delaying the formation of shocks that create extra drag. Why is this important? Because the aerofoil, or anything with a camber for what matters, like a delta wing, accelerates the airflow on the upper surface and slows down the flow on the lower surface. If the leading edge is tilted in respect to the flow velocity, only the component of the speed perpendicular to the leading edge actually increases or decreases. In fact, the camber forces the air to accelerate to flow upward and above the wing, but the edgewise component doesn't see any change in thickness, so it's not affected. Please notice that this is a geometric formalism, but it explains what happens for real. What happens on the upper surface when the perpendicular component is increased? Better, what happens to the total velocity? Well, it turns inward, toward the fuselage. Look at these tapes on the wing of the XF-92A. You can clearly see that this one is tilted inward. So if the tilt happens in the middle of the wing, no big deal, but what about in proximity of the wing root? The air can't turn inward because there is a solid surface forcing it to go straight, that is the fuselage wall. Since we are close to the speed of sound, the airflow is energetic, and to deviate it and make it straight, the fuselage must exert quite a pressure on the air. This pressure actually propagates along the wing, causing small shocks that tend to coalesce at the tip of the wing in larger and potentially dangerous shocks, like the one we have seen before. All this convoluted airflow sucks energy to be generated, and thus extra drag is generated. Now we know the problem, but what is the solution? Very easy, move a piece of the fuselage out of the way, making it thinner to let the flow move inward with no disturbance. This is what is usually referred as pinching or Coke bottle shape. The size of the fuselage may increase when the flow slows down toward the back of the wing, because the flow, in this case, will naturally want to move outward. How much do the fuselage need to be narrowed? Here is Whitcomb's second stroke of genius. He came up with a simple geometric description for the sonic area rule. If a wing-body combination, including the external stores, is so designed that the axial distribution of the cross-sectional area normal to the airflow is the same as that of a minimum drag body, then the wing-body combination will also have the minimum drag. Easy, isn't it? So in practice, in cutting a lot of corners, take a slender body that gives the minimum drag attainable in transonic conditions with the same length and the same volume as the plane. Cut it into slices like a salami and measure the area of each slice. Do the same to the plane. Make sure that the plane slices have the same area as the body slices in the corresponding positions. Since a slice that includes the wing must have a large area, the only way to reduce it is to narrow the fuselage. So what happened to the YF-102 after applying the area rule to the design? The first modified prototype flew on the 20th of December 1954. During its second test, it went supersonic in level flight. In the following days, it reached the speed of Mach 1.25, satisfying the Air Force requirement. The first production plane flew in June 1955 and entered service in April 1956, starting a long and honorable career. But this is the subject of the next video. In the late August of 1964, if you had walked along the flight line of the Da Nang Air Base in Vietnam, you could have seen something very, very strange. At first it might have been confused with something else, but to the trained eye, a row of F-102A painted with a green and khaki livery must have seemed a very bizarre appearance. Some questions would have come naturally to mind. The F-102A was an interceptor designed to counter the Soviet nuclear bombers. Why was it in Vietnam? Why was it painted green? Why the planes were actually part of an interceptor squadron? To answer these questions, we have to tell a story first. Welcome to Millennium 7 Style, the channel that helps you make sense military history and military technology. Please stay with me till the end, because the stuff that we discuss here is not easily found anywhere else on YouTube. In 1950, the United States Air Force issued a specification for the ultimate interceptor, expected to enter service in 1954. The plane should have been the American reply to the new Soviet bombers, capable of reaching the United States soil through the North Pole. There was a competition, and the winner was a revolutionary plane, the F-102A Delta Dagger, or Deuce, as everybody referred to it. We told the story of its development in another video, and it was an exciting story because amid apparently impossible problems, new scientific advancements, and expat German scientists, it gave birth to a world first, the first Delta Wing combat plane to enter operational service. First operational squadron with F-102A was activated in April 1956. The production happened on a very large scale, and by the end of 1958, almost 900 F-102 had been produced. At the top of its employment, there were 51 operational squadrons, one of which part of the Greek Air Force and two part of the Turkish Air Force. The United States Air Force employed the plane during the 60s and well into the 70s. Toward the end of the period, it was transitioned to the Air National Guards unit, where the last units were decommissioned in 1976, while the Greek and the Turkish Air Forces kept the planes operational till 1979. The plane configuration has been remarkably stable throughout its life, with only minor updates to the wing and the electronics. The primary mission of the F-102 was to defend the North American airspace from the Soviet bombers, so the bulk of the planes was deployed to cover the northern approaches of the American continent, from Alaska to Greenland. Actually, some squadrons with the same missions were deployed in Europe and in Japan. The forces deployed in North America were coordinated by the SAGE system, which could optimize the management of the available resources, controlling the interceptors, but also the surface-to-air missiles like the Bomark. Actually, in all seriousness, the story of the SAGE network is an epic technology story, and one day we will tell it. The plane needed to be able to take off quickly and fly fast, typically supersonic, towards the target. It had to engage it with weapons effective enough to shut down a large target capable of absorbing quite a lot of damage. And for this reason, the F-102 was equipped with the first generation of guided air-to-air missiles, the Falcon family. A plane and its pilot would have been in QRA duty, a condition in which the pilot and the plane are ready to go in minutes. There would be a hangar with facilities for the pilot and ground crew close to the runway. The base command and control center would have received by teleprinter connected with SAGE the mission parameters. The pilot would have been quickly briefed while taxiing, and once airborne, the F-102 would have been directed toward a target. Standard procedure was to order the pilot to follow a bearing at a specific altitude and speed. However, many planes were equipped with the SAGE data link. Once activated, the plane autopilot could receive bearing and altitude directly from the SAGE computers, being directed automatically toward the target, leaving the pilot free to use the radar or the primitive infrared search and track mounted just above the nose to locate the target. Yes, because the radar track had a rather high incertitude. The SAGE long-range radars were low-frequency sensors that had a long range in exchange of a poor accuracy. The incertitude could be easily more than a dozen miles. So very high. It was up to the pilot to locate and attack the bomber with its own sensors. The F-102 radar had a short range, but long enough to search the patch of the sky where they had been directed by the control. If the radar was jammed, for example by the release of chaff from the bomber, the F-102 had the option to use the infrared search and track. Actually, the radar could be slaved to the infrared search and track in order to achieve a passive track of the bomber, eventually using the radar just before firing a semi-active Falcon, or just keeping totally passive with an infrared guidance 1. Once the target was located, the pilot would normally have tried to execute an attack from the stern. Because of the short range of the Falcon missiles, a frontal attack left very little time to the pilot to react, while an attack directly from 6 o'clock would have exposed the plane to the fire of the tail guns, which were still in use at the time. So the preferred solution was an attack from the stern, closing into the bomber from 4 or 5 o'clock or 7 or 8 o'clock in respect to the bomber. And the fighter was expected to repeat the attack until the bomber was downed before moving on to another target. Despite the fact that the plane was built for speed and supersonic flight, it turned out to have a surprising quality. It was very maneuverable. The low wing load allowed for very tight turns, so the plane turned out to be an excellent energy fighter or an excellent dogfighter. This meant that it could be used to contrast directly the enemy fighters, and at the time the Air Force indeed had an enemy that needed contrasting. During the 60s, the United States' involvement in the Vietnam War was growing. The more planes and helicopters were flying around, the more fighters for combat air patrol and bomber escort were necessary. Since the F-102 seemed to sit around just waiting for an offensive that was never coming, a few of them were tasked to contribute to the Vietnam War effort. And there, something unexpected actually happened. In 1962, the radar coverage started detecting Ilyushin-28 bombers flying from North Vietnam, so the F-102 were deployed as a defensive measure, flying combat air patrols to prevent incursions and defend the South Vietnam. However, it was only when the planes started to fly as escort to B-52s, which at the time were flying the famous arc-light bombing missions, that they encountered the enemy. It was during these missions that the only loss of an F-102 to enemy fighters actually happened. The Deuce did not really score any air-to-air win because the Vietnamese Air Force hardly engaged them, preferring easier targets. So the career of the Deuce in Vietnam in its role was relatively uneventful when an interesting idea started to emerge. The Ho Chi Minh Trail was a belt of jungle path where men with bikes and animals connected the north of Vietnam with the south and the Mekong Delta, passing through Laos and Cambodia. Viet Cong supplies slowly flowed through the jungle in a very decentralized manner, very difficult to attack and choke. It was in this context that someone realized that the F-102 had an infrared search and track and infrared-guided Falcon missiles. The infrared search and track turned out to be capable at night of detecting heat sources like campfires or men moving in the jungle against the cold backdrop of the ground. And what was more surprising was that the Falcon B infrared missile did lock to ground targets, and being slow movers, they turned out to be relatively easy to hit. So the plane abandoned its beautiful white livery for a green and brown jungle camouflage. The missions were technically successful because extended the dangers for the Viet Cong in the 24 hours. The problem was that they were also extremely expensive because a complex and sophisticated Falcon was used to hit a group of people near a campfire. The F-102 also had unguided rocket mounted inside the doors of the missile bay that could be used to shoot ground targets, and indeed they were. So this kind of air-to-ground activity kept going for a few years, but it did not expand, it did not become a further full-fledged statutory mission for the plane. While the F-102 was busy patrolling the skies over Vietnam or chasing targets in the jungle, Convair was busy developing the plane. The F-102 managed to satisfy the Air Force specification, but only just. the Air Force would have liked more speed, and the interim electronics was acceptable, but not fully up to the expectations. So as soon as the F-102A entered production, Convair started working on the F-102B, which was going to be the real ultimate interceptor. This development brought into being one of the most beautiful planes of all time. But this is the subject of the next video. Welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. Please stay with me till the end, because the stuff that we cover here are not easily found anywhere else on YouTube. When the F-102A Delta Dagger, that used for everybody, entered service in 1956, it was a revolutionary plane, but nothing could hide the fact that it was just barely compliant with the Air Force specifications. In fact, at the end of 1951, difficulties with the fire control system and the engines de facto split the program in two. The F-102A had to be an interim solution, while the F-102B, being the fully compliant plane, expected to enter service at a later time. Now, difficulties with the F-102A forced Convair to divert resources from the F-102B, which actually fell even more behind. So, in one of the most spectacular applications of the principle that nothing is more permanent than a temporary solution, about 1,000 F-102A were produced. However, despite the numbers, the F-102 shortfalls as an interceptor were rather clear. The plane speed was limited to Mach 1.25, mostly because of the interim engine, the Pratt & Whitney J57, which did not have the adequate thrust. And also the plane fire control system was not providing all the functions that were required, being a simplified version of the original specification. So, something better had to be developed. For the F-102B, the so-called Cook-Craigie approach was taken. No prototype was built, but a limited number of production units had to be delivered so changes could be incorporated directly on the production line. This could shorten the time to delivery if there was just a limited number of changes to make, but it risked having a relatively large number of underperforming planes already built that might have required a complex and expensive retrofit once a stable configuration was reached. If now you are thinking to a more modern plane, I won't stop you. However, by 1956, the development of the F-102B was moving forward at a steady pace, and the plane that was taking shape had a clear lineage with the F-102A, but also so many differences that in June 1956, it was renamed F-106A, the Delta Dart. The first F-106A rolled out of the production line in December 1956. It flew for the first time in the Boxing Day of 1956, a clear indication of how rushed was the entire program. And as soon as the plane took the air, problems started. So during the first flight, the turbine of the new J75 engine performed irregularly, the air brakes opened but not closed, and still the MA1 fire control system was missing and there was some ballast in its place. But these were not the main problems, there was more. The early tests measured the speed of Mach 1.9 at 57,000 feet, much better than the F-102, but still below the expectations. What surprised everyone, including Convair, was that the supersonic acceleration was abysmal. It took 4.5 minutes to accelerate from Mach 1 to Mach 1.7 and another 2.5 minutes to accelerate from Mach 1.7 to Mach 1.8. So after all, the number one reason for adopting a delta wing was to have a good transonic and supersonic behavior. And then this happens? This was totally unexpected. Convair's engineers were seeing the ghost of what happened a few years before with the F-102 coming back to haunt them. Needless to say, the United States Air Force was not happy at all, and once again the whole program was at risk. Luckily, the problem this time was not so bad and did not require the genius of Whitcomb to fix it. Even if Whitcomb was still working for Convair at the time and the F-106 bears his signature in various areas. This time, changing the air intakes was enough. The lips of the intake were thinned down and their capture area was increased, increasing the airflow going through it. The increase in size is relatively easy to understand. The J75 P9 engine could handle more flow than it was fed, so it didn't produce all the thrust it was capable. Eventually, the P9 engine was replaced by the P17 version, which was rated for 76.5 kN dry and 109 kN wet. The reason why thin intake lips helped is a bit more difficult to understand. So, air intakes and propulsion in general are very complex subjects, but as usual, let's try to explain in an intuitive manner. So the main function of the air intakes is to recover pressure. The air moving toward the plane has a lot of kinetic energy, and it is desirable to have this energy converted into pressure at the entrance of the engine. The more pressure there is, the more will be available to be added to the engine work, the more will be available to expand the gas through the nozzle to generate thrust. At supersonic speed, the air decelerates through the formation of shock waves. That is a thin layer where speed is abruptly diminished and pressure increases. When actually a shock reaches your ear, you hear what is normally called a sonic boom. In front of a blunt shape, the shock is very strong, the air deceleration is very high, and it stays at a distance from the shape. The stronger the shock is, the more energy is wasted, and the lower is the pressure behind it. Strong shock waves dissipate a lot of energy and create a lot of drag. Weaker shock waves are more efficient and create less drag. And the way to have a weaker shock is to use a pointy shape. The shock will be practically attached to the shape and it will be weaker. There will be a better pressure recovery and a lower drag. An even better improvement is to have the flow slow down through multiple weaker shocks and the mobile ramps visible on the intake do just that, with the plus of adjusting their position to avoid shock interference among each other and with the plane boundary layer in different flight conditions. At the end of the day, the difference was not small at all. In the case of the F-106, the improvement in pressure recovery was estimated between 15 and 18%, and the acceleration time from Mach 1 to Mach 2 went down to 3 minutes. So while everybody was having a sigh of relief because the program was saved, like it always happens with high-tech projects, problems were not over. The fire control, now dubbed MA1, was chronically late and it became available only in 1957 in the first production version, but it will keep receiving updates during all its operational life. The cockpit configuration was changed a few times before stabilizing, with different types of instruments and different position of the control stick. the radar control, the fire controls, and the horizontal situation indicator, which actually was a navigation aid, not a video game screen. Other defects had to be ironed out during the pre-production and the first years of operational service, like fuel flow deficiencies, electric generations issues, and a canopy accidentally jettisoned in flight. Even the ejector seat was changed and modified a few times before becoming safe and reliable, not without killing some pilots. Also, the wing, at the beginning identical to the F-102, was involved in several iterations, where boundary layer fences were added and removed, slats were adopted, camber changed, and wingtip twist updated to the point of obtaining relevant differences between a unit and another about the way the plane handled. The interesting thing was that rather than fixing everything on the prototypes, thanks to the Cook-Craigie approach, every batch of planes had a different set of updates, and it was different from the others. The Air Force in 1960 will have to launch a program to bring all the planes to the same standard, at least for the fire control unit, and the logistical nightmare of having so many different versions. Because of all these hiccups, the Air Force grew increasingly cold toward the plane, even because the F-101 had been introduced as a temporary measure, and at the end of the day it was doing pretty well. Once again, the program risked being outright cancelled. This did not happen, but the number of planes on order was greatly reduced, with the motivation of this actually being just the high tier of the air defense system. And we will see it will be a justified position. Only 260 planes were ordered, and later 35 planes used for tests were converted to the stable standard and handed over to the fighter squadrons. Including the double-seaters for training, about 340 F-106 were built, equipping 14 squadrons. The aircraft was slowly replaced by the F-15 from the beginning of the 70s, but it served for a very long time after that, the last being retired in 1988. Stop there, we are not even nearly finished yet. The best is yet to come. The plane served briefly in Korea and Germany, but the bulk of the deployment was always in the continental United States, under the Air Defense Command, and there was a very good reason for that. The F-106 had a very close integration with the SAGE system. The SAGE was a chain of radars and command posts all connected and integrated together, covering the northern approaches to the North American continent. The purpose of the system was to meet a Soviet bomber offensive with a coordinated effort, employing all the available assets in an optimized way. The story of the SAGE is not only one of military technology, but also one of the first attempts to use computers to coordinate and automate a battle space. It is actually a story that will serve a long video in the future. The assets available to SAGE were guided missiles, like the Bomark, piloted interceptors, like the F-102 Deuce or the F-101 Voodoo, and anything in between, like the F-106 Delta Dart. In fact, after taking off, the SAGE system could take control of the plane by feeding the bearing and the altitude to the autopilot, using one of the first military data links. With a range of many hundred miles. The plane could literally be flown remotely toward the target. Since the long-range and low-frequency radars integrated into the SAGE system could not pinpoint the location of a target, it is actually a physical limitation connected with the frequency and the way electromagnetic waves do propagate, the plane had to identify the exact target position with its own sensors. While on the F-102 this function was left to the pilot, on the F-106 it was a task of the AM-1 fire control system. The plane could be handed the approximate position of a target by the Sage, locate it to precision with its own sensor, and attack it automatically, firing the weapons and placing the plane on an escape route, all without the pilot participation. The only task left to the pilot was to check the proper functioning of the systems, ready to pick up in case of malfunction. In the context of the Sage, the pilot was really needed only for takeoff, landing, and as a backup system, and for this reason a tactical situation display between the pilot's feet showed a moving map of the route across the ground during the intercept. As on the F-102A, the armament was housed internally in a large weapons bay that was closed by pneumatically operated double folding doors. The original armament was all missile. There was a single Douglas Air 2 Genie unguided missile equipped with a 1.5 kiloton nuclear warhead. This was complemented by 4 Hughes IM-4E Falcon radar homing or IM-4G infrared homing air-to-air missiles. The F-102A had unguided 2.75 inches missiles mounted on the weapons bay doors, but these were not retained on the F-106. The Genie missile was carried in the rear half of the missile bay. It was powered by a 163 kN Thiokol Tu-389 rocket motor, and it was unguided. It relied on the nuclear warhead to ensure a kill, and since there was no guidance system but just a safety mechanism to prevent premature detonations, it could not be jammed. Launch weight was about 360 kilograms and maximum velocity was Mach 3.3. Snap-out rear fins gave the missile stability during flight. The range was about 8 miles and flight time to target was about 12 seconds, and the effective blast radius was estimated to be about 300 meters against a heavy bomber. The Falcons were a conventional warhead adaptation of the nuclear-tipped AIM-26A Falcon. The 2 semi-active radar homing AIM-4E Falcons were carried in the forward half of the weapons bay, whereas the AIM-4G infrared homing missiles were carried in the rear half of the weapons bay, stored on the side of the Genie. All Falcon missiles were contact fused, with the fuses located on the leading edges of all 4 fins, so that a direct hit on the target was needed to score a kill. The Falcon missiles could be launched in a single salvo or, more commonly, in pairs. Because the aerodynamic range of the AIM-4F was greater than the range of its seeker, the IR-guided AIM-4G was the preferred means of attacking a fast-moving target. At high closure speed, in a head-to-head situation, for example, the AIM-A1 fire control system would present 2 separate firing solutions, one for the AIM-4G and the other for the AIM-4F. If all 4 missiles were to be fired, the 4Gs were fired first so they would not inadvertently lock onto the radar-guided missiles rather than the target, which was also the reason why the 4F pair was carried in the rear bay. It was not possible to fire the missiles one by one, because the pneumatic system that had only enough high pressure stored for 3 cycles of the armament system. So the original F-106 only had 3 shots available, 1 Genie, 1 pair of IM-4F, and 1 pair of IM-4G. The last F-106 was delivered in July 1961, but as we have already pointed out, the plane kept receiving improvements and updates throughout most of its career, something that was needed for the F-106 more than for other planes, because the Cook-Craigie approach. The fire control system, in particular, kept improving its reliability and performance throughout most of the plane career. By 1963, all the planes had been equipped with a retractable infrared search and track in front of the cockpit. One may wonder, what was the use of an infrared search and track for a highly automated machine like the F-106? In 1961, the Air Defense Command had budgeted about 80 new aircraft to cope with the attrition rate and fill the gaps. The original idea was to reopen the assembly line for the F-106. However, the Air Defense Command had heard so much about the F-4 Phantom II, the new US Navy two-seat interceptor, and so they pushed the Air Force to hold a competition between the F-4 and the F-106, performing the same missions. The competition result was that the F-4 system had better performances and were more reliable. Its radar could lock on targets at a much longer range than the F-106. However, something utterly unexpected happened. In air-to-air combat against the F-106, the Delta Dart almost systematically defeated the Phantom. The idea that the F-106 could be a versatile interceptor rather than a guided missile with a backup human pilot started to emerge. For the record, after the competition, the Air Force will go on acquiring the F-4 for the Tactical Air Command, and the Air Defense Command will receive no planes. So, having surprised everyone with its dogfighting abilities, there were serious thoughts about sending the F-106 to Vietnam, which in the end did not happen. However, the idea of equipping the plane with what was necessary and useful for air-to-air combat went ahead. The new emerging scenario was that of a bomber flying at low altitude below the radar coverage, maybe with some escort fighters. In this case, the Sage could not automatically guide the interceptor, and the whole idea of exploding a nuclear device close to ground deep in friendly territory, well, wasn't brilliant at all. The infrared search and track was used particularly at night to search for the bomber's infrared signature against the cold ground. Also, since the Genie missile was no longer useful in this scenario, it was replaced with something much more classic, a 20mm M61A1 Gatling cannon housed inside the weapons bay in place of the Genie. Only 75 F-106 were equipped with the gun. Those that were could be distinguished by a ventral bulge housing the barrels. Technical constraints limited the fire rate to 4,500 rounds per minute, anyway enough to empty the 650 rounds magazine in less than 9 seconds. The F-106 served for a long time, the last flying units being decommissioned in 1988. At the time, the F-106A had the distinction of recording the lowest single-engine aircraft accident record in the Air Force history. Other than its main mission, it was used by NASA for research programs and after decommissioning as a target drone for weapons testing. As we said, a limited number is still in store at Davis Mountain, waiting for a call that will never come. Or will it? If you like this video, you will be interested in the videos that are going to appear beside me. In the meanwhile, please stay safe. Thank you very much for watching and see you next time.